I'll talk about security analysis of multilinear map of the integers. This is a result with collaboration with Hyung from NTU Singapore. And this is the outline of my talk. First, I briefly overview about our contribution. And next, I will introduce a new hard problem. We called it as a best partial approximate common divisor problem, actually which abstract system parameters of multilinear map of the integers. Next, main contribution will be presented. In particular, we propose a square root attack for system parameters of multilinear map of the integer. Actually, this is attack algorithm for MPSD problem. We also point out some weakness point of system parameter generation method given in multilinear map of the integer paper. And I present our experimental result. Finally, I give a concluding remark. This is a definition of multilinear map. Actually, this is actually definition of a symmetric version of multilinear map. A multilinear map E is defined over several copies of cyclic group G, and the target is also cyclic group GT. And actually, it is not hard to construct multilinear map. However, to use multilinear map for cryptographic purpose, we have to care about security. It means it is hard to construct multilinear maps satisfying cryptographic assumptions such as DLP. And it has been an open problem for a long time. Last year, Garg et al. Proposed the first candidate multilinear map from ideal lattices. Actually, what they propose is not an ideal multilinear map. What they propose is just approximate multilinear map. And last year, crypto, the second construction is proposed by Coron et al. Actually, they used a different kind of mathematical structure, the integers. Right after first proposal of candidate multilinear map, numerous applications are proposed. You can see, there are several applications like this. However, there are very few analysis on multilinear maps. So here is our contribution. We propose an improved attack for public parameters of approximate multilinear map of the integer. Multilinear map is also called gradient encoding system. Then here is a table to compare our result, our attack algorithm's complexity, and previous best attack in terms of error size low. We also point out that the zero testing parameter generation method given in multilinear map paper over the integer paper does not provide sufficient entropy. This significantly weakens the security of multilinear map over the integer. Let me introduce a new hard problem. Before that, let me start with well-known ACD problem. Here, P is large script prime, and X0 is a multiple of prime P, and other Xj's are almost multiple of P. Here, Rj's are small errors chosen in this range. Then ACD problem is that given Xj's, find script prime P. And PACD problem is given X0 and Xj's, find P. To make PACD problem hard, we have to carefully choose the size of X0, bit size of X0 and bit size of P. And as per the error size rule, we have to care about Chen and Nguyen's attack because it is best attack in terms of error size low. The idea is very simple. Just compute GCD of X0 and this product, and you can easily check this product covered all possible errors. So it's an exhaustive search. And it costs 2-3 row operation. However, if we use a classical FFT technique, fast Fourier transformation technique, we can reduce complexity to 2-3 row over 2 with a similar storage size. And we can extend this PACD problem as follows. Here, X0 is a product of several primes, and other X's are unique integer less than X0, satisfying these equations. Here, Rij's are small errors contained in this range. And problem is that given X0 and X's, find a non-trivial factor of X0. And we can show that this problem is harder than PACD problem. Then from now, I will explain, I will use new notation of Chinese remaindering. And this CRT notation denotes a unique integer x contained in this range satisfying this equality. So if we use this notation, previous problem's instance can be written by this formula. Then now we are ready to explain our new hard problem. New hard problem's instance is almost the same as before. Only difference part is this unknown factor q is produced in all samples. Then unknown integer q is cumbersome in attacker's view because we cannot directly apply to Chen and Nguyen's attack. Because to apply Chen and Nguyen's attack, we have to subtract errors, but if we do not know about q, unknown q, then we cannot subtract directly. So we cannot directly apply Chen and Nguyen's attack. Then let me explain about system parameters of multilinear map over the integers. System parameters of multilinear map contains two different kinds of public parameters: zero testing parameters, re-randomization parameters. Actually, the reason why I explained about the MPHD problem is to generalize these system parameters. Zero testing parameters is vector, and actually vector, each component of vector looks like this. Here, Q looks very complicated, but we can just assume that this Q is unknown vector. So we can consider this zero testing parameter as an instance of MPHD problem. Similarly, we can consider the randomization parameter as an instance of MPHD problem. So from now, let me forget about system parameters of multilinear map over the integer for a while. And let me just focus on instance of MPHD problem. We can show that MPHD problem is harder than PHD. However, the reduction is not tight. It means in practice, there could exist some attack algorithm which break MPHD problem much faster than PHD. Then here is, this is a table to compare best attack algorithm for MPHD and PHD. And you can easily check there is some gap. Then our goal is to reduce this complexity to almost similar to this complexity. Let me explain Coron et al.'s attack algorithm for MPHD. Actually, Coron et al. Does not mention about MPHD problem. What they propose is, they just proposed an attack algorithm for system parameters of multilinear map over the integer. But we can easily generalize their attack algorithm for MPHD problem. It takes x0 and x1 and x2 as input. Here, x0 is the product of several primes, and x1 and x2 are samples. If first compute u like this, then u is equal to R1 or R2. Then unknown factor q is removed. So the remaining part of attack algorithm is almost the same as Chen Nguyen's approach. Just compute GCD of x0 and this product. Here, this product covers all possible R1 and R2, so it's a kind of exhaustive search too, and for all possible R1 and R2. And maybe computation costs too low, but if we use FFT technique, we can reduce complexity to low. Then our goal is improve this attack. Let me explain our attack algorithm. Before that, let me briefly explain some function f which will be used in our attack algorithm. Here, x's are samples. Given several samples, consider this function f. It takes m-bit vector b as input, and its output is just subset sum of samples according to the vector v. And if we compute mod p1 of function value, then the result is like this, and you can check that this resulting value is contained in this range because the RJs are very small, smaller than mod p1. Here, important thing is domain size of f is exponential in m. However, range size is polynomial in m. Actually, range size of composition of a function f and mod p1. So if we increase m, then we can find the appropriate m such that domain size is larger than twice of range size. So if we select such m, then we can expect this probability is larger than or equal to 1 over 2 by using P-genome principle. This probability means if we choose random vector b, there exists another vector b prime satisfying this equality. Actually, for example, if we choose m is slightly larger than rho, then we can expect this probability. This is a description of our attack algorithm. Input is x0 and m samples. If choose random vector b, m-bit vector b, then it computes GCD of x0 and this product. Here, this product covers all possible m-bit vector b prime. So trivial computation costs 2 to the m operation. But if we use FFT technique, we can reduce complexity to the 2 to the m over 2. But until now, I didn't mention about the success probability. I only checked the computational complexity. So if we set m is slightly larger than rho, as I said before, we can expect this probability is larger than or equal to 1 over 2. And this equality implies that here this product is multiple of P1. If this is multiple of P1, the result of this GCD computation will be P1. So success probability of this algorithm is larger than or equal to 1 over 2. However, there is some subtle issue we have to care about. There is some possibility that resulting output is x0. I mean, previously I said this equality hold mod P1, but as mod P2, mod P3, there is same probability. So there is some possibility that this equality hold mod x0. So it means this product will be a multiple of x0, then GCD, result of GCD will be x0. In fact, the previous CLT attack has the same problem. To resolve this problem, we can shorten m, so this equality hold at least one, but not all possible pi. Roughly, one of square root m fraction is sufficient by birthday paradox. So overall, the success probability of our attack algorithm is 1 over 4. And complexity is roughly 2 to the rho over 2. Then let me say about some weakness point of zero testing parameter generation in multilinear map over the integers. This is zero testing parameter, one component of zero testing parameter. Here, Hij plays a role of errors in MPHD problem. However, in the multilinear map of the integer, this Hij have to satisfy this two bound. To generate such Hij satisfying this two bound, Coron et al. Proposed some methods. Let me explain their method. Here, HAI is matrix, and I is identity matrix, and I is also matrix, which consists of -1, 0, 1 in entries, and pick HI randomly as either HAI or H transpose, and then just compute H matrix as a product of HIs. The method is very simple, and this method guarantees that resulting matrix H satisfies this two bound. However, this method does not mention about the security. For the security, we need low bound or average bit size of Hij. And upper bound is not important for security. And actually, we implemented to check average bit size. Then our experimental results show that average bit size of Hij is very smaller than expected. Then what's the problem with current H matrix generation? Let me consider the following case, which frequently occurs. This matrix and this matrix can be one of HI matrix. HI matrix is one of HAI or its transpose. So in this case, if we product these two matrices, this is a resulting matrix. If we consider operator norm of this matrix, and operator norm of this matrix is almost equal to addition of operator norms of these two matrices. It means, in this case, additive bound is enough for operator norm of resulting matrix. However, the authors of multilinear map of the integer used multiplicative bound in order to guarantee these two bounds. It means even if they used multiplicative bound, in fact, operator norm just increase additively only. So average bit size also very slowly increase in this case. So this is a problem why the previous method does not provide sufficient entropy. Then how to fix? It's easy to fix. Then just multiply HAI when I is odd, and its transpose when I is even, instead of randomly choosing between HAI and its transpose. And also, we have to increase beta to be larger than lambda. And we also checked, we implemented, and our implementation shows that this modified method increase Hij's average bit size very quickly. This is our experimental result. We implemented our attack and applied to the system parameters of multilinear map over the integer given in the paper, except for the zero testing parameter. Because in the original CLT paper, author presented implementation result based on heuristic optimization using a single zero testing parameter, a single integer zero testing parameter in consonant to zero testing vector in the main scheme. So actually, our attack algorithm requires several samples, but so it cannot apply to this implementation parameter, so we slightly modify the implementation parameter. This table showed our experimental result, and this table shows our attack algorithm break system parameters of multilinear map over the integer very quickly. For example, for the 62-bit security, it takes less than a minute. So, however, if we apply our attack to modified method of H matrix generation, then modified methods seem to secure against our attack. And this is conclusion. We proposed the attack algorithm and point out some weakness point. And yeah, that is open problem. Yeah, that's all. Thank you.